Welcome back, Calculus. There's another section in the limits chapter. We're going to talk about continuity and piecewise functions. So you can have that in your notes. The objectives are to determine if a function is continuous, evaluate piecewise functions, and evaluate limits of piecewise functions. So the piecewise function is going to come back a little bit from pre-calc, and a lot of the old functions that we've graphed before, we're going to need those skills here. What makes a function continuous? So to be continuous, there's kind of like three things that need to happen. So a function is continuous at some value c if the three of these things happen. One, the function evaluated at c is defined. So if we have a whole or an asymptote, we're not continuous. Now the limit of the function as x approaches c needs to exist. So if the limit doesn't exist, then the function is not continuous. And then the third thing that needs to happen is that 1 and 2 agree with each other. They're the same value. In other words, the limit of the function as x approaches c is equal to f of c. So if those three things happen, we say that a function is continuous. FYI, a function is continuous everywhere if it is continuous at every x value in the domain. Okay, so this is when a function is continuous at one point. These three things need to happen. And if it's continuous at every point, then we say the function is everywhere continuous. So what is a discontinuity? What does it look like? So if f of c is not defined, so at some value c, the function is not defined, call this c. So at this point c, maybe there's no point there. So then the function would not be continuous at c. What if the limit doesn't exist there? So a lot of ways that could happen. You could have the left-hand limit from c approaching one value, and then once we pass c, it kind of jumps to a new value. So that would be an example of a function where the limit doesn't exist. Of course, you could also have an asymptote here too, right? So something like that. And maybe the limit exists and the function exists, but they don't equal each other. So at the value c, my limit's approaching this value. However, the actual value of the function is down here. So that's a situation where the function doesn't actually approach what the limit's approaching. And that could have also happened that maybe you had an asymptote where it's going to infinity, and maybe we put a point right here, and in that case, the limit's going to infinity where there's a point there. But anyways, examples of discontinuity. This is not something you need to write down, but it's something to just try to understand. Continuity in an open interval. This is like a book definition, and it's good to get a feel for like how books write definitions, because they're very specific and they're powerful. And it's if you can kind of like unravel what it's saying, it's a good skill to have going down the line. But a function is continuous on an open interval a to b. So this is not a point a comma b. This is the interval a to b. If it's continuous at each point in that interval, and a function is continuous on the entire real line, it's everywhere continuous. So that's what I was saying before about being everywhere continuous. So on an open interval from a to b, if the function's continuous everywhere in here, then we could say it's continuous on that interval from a to b. And if the function is continuous for all real numbers, then the function's everywhere continuous. So, two types of discontinuity. Removable discontinuity And you can copy this down. We can redefine or define f of c to make f of x continuous. When I give you guys a picture of this graphically, I think it'll make a little bit more sense. But it's when I can redefine one value at that c value to actually create the continuity that we want. And sometimes, in non-removable discontinuity, we can't just move f of c around and have now a continuous function. So I'll look at an example of what that is graphically. But for now, this is how we're going to talk about the two types of discontinuities, removable and non-removable. So, part of the objective is to graph piecewise functions, and let's see if we can do that. Well, I don't want to hold you off on this too long. So, here's a function that's not continuous. Now, if I were to take this point and move it to that point right there, it would now become continuous. So that is what we would call removable discontinuity. We can just remove one point to kind of to make the limit exist. So I can take the c value, and if I just redefine it, instead of equaling, say, 1, made it equal 2, then the function would be continuous. This is a removable discontinuity. One point will actually fix that discontinuity. Non-removable, say you have a jump, for example. Even if I take this point here and move it down here, it doesn't fix the fact that it's still discontinuous. So no matter where the point is, moving one point doesn't move the infinite points that is making a discontinuity. So this would be a non-removable. And an asymptote would also be non-removable because you can't move one point to fix that. So down to this graph. We have a piecewise function. Let's see if we can sketch it and then decide if there's any discontinuities and what type they are. So when x is less than 1, it takes on the role of the function x plus 3. So 1 is right here. And as long as x is less than 1, it takes the function x plus 3. So x plus 3 is a linear function. You can think of it as a slope of 1, a y-intercept of 3. And so if it's got a slope of 1, it's going to go up 1 over 1. I'm going to put an open circle here because once x equals 1, we have to jump down to negative 2. But if that's the slope, I can kind of go backwards. So as long as x is less than 1, that's what the function looks like. So that is the first part. And then once we get to x equals 1, it shoots down to negative 2. And then once x becomes bigger than 1, it becomes a function negative x plus 5. If you want to think of it as negative 1x plus 5, that's a function with a y-intercept of 5 and a slope of negative 1. So 1, 2, 3, 4, 5. So the function would look like this, but it doesn't start until I get to 1. So that's going to be right here at negative 1. Or if you plug in 1 to this, you can find out what the y value is. Negative 1 plus 5 is 4, so at 1 comma 4, the function starts there. And it's going to have a slope of negative 1, so it's going to go down 1 over 1, down 1 over 1, down 1 over 1. So that's what the function looks like, this piecewise function. And the question was, are there any discontinuities? Well, yes. If we look at our kind of test here, does f of c exist? And yes, if I, in this case, that value is 1, that's the value that we're kind of worried that there might be discontinuity. And f of 1 does exist, so it equals negative 2. So that's true. Does the limit of the function as x approaches 1 exist? Well, yes, as x approaches 1, it's 1, 2, 3, 4. The limit from the left and from the right is both approaching 4. So the limit exists, the function exists, but the limit and the function are not the same point, are not the same value at c. So does f of 1 equal the limit of the function as x approaches 1? And the answer is they do not equal each other, right? Because -2 is not equal to 4. So the limit does not exist at that point, so we do have a discontinuity. And this is the removable type, because if I could just take this blue point and move it up, the function would then become continuous. So this is what we call removable discontinuity. Right. So all we have to do is redefine this point. Instead of having it equal -2, we just would need it to equal 4. And if we just made that 4, we would then have a continuous function. I'll leave the color coding up for you. All right. Another example. Given this piecewise function, is it discontinuous anywhere? If so, where and what type? By the way, I want to say this. Yes. When you say yes, where is it? And that's at x equals 1. So make sure that you tell me where the x value is that the discontinuity is happening. All right, so this function takes on the form -2x minus 3 when x is negative or less than 0. And then when x is bigger than 0, it takes on this quadratic function, x minus 1 squared minus 1. So -2x minus 3 has a y-intercept of -3. It's going to be an open circle because we're not, when x is equal to 0, we have to go to this other function. And the slope is -2, so that's, instead of going down 2 over 1, down 2 over 1, because I got to stay into the left of this point, I'm going to go up 2, backwards 1, up 2, backwards 1, up 2, backwards 1, up 2, backwards 1. And that's going to give me -2x minus 3. And then what happens here? Well, this function right here is a quadratic function in vertex form. So this is the vertex form of a parabola. So in general, I think they use h and k here. X minus h squared minus k. Actually, I think it's plus k, where h and k is the vertex. So in this case, the vertex is going to be 1 comma -1. So it's x minus 1, so h is 1, and then instead of having a plus, we have a minus h, so the k value is -1. So 1, -1 is the vertex. It's going to be opening up because it's positive, so it's going to look something like this. And then when I go to the left, if I'm not sure that it's going to go right here, which I'm pretty confident it's going to go to 0, 0, you can just plug in 0 and to find out what the value is at 0. So if I do 0 minus 1 squared minus 1, 0 minus 1 is -1, squared is 1, and 1 minus 1 does equal 0. So we get this point here, 0, 0. And that's going to be a closed-in point because we have the inclusive inequality. So now the question is, are there any discontinuities? Well, let's see. Does f of 0 exist? F of 0 equals 0, so it exists. Does the limit as the function approach 0 exist? And the answer is no. The limit from the left is approaching -3. The limit from the right is approaching 0. So the function is discontinuous at x equals 0. And in this case, even if I were to move this point right here down to here, it still would be it still would not be continuous. So this is a non-removable discontinuity. Okay. So one-sided limits. luckily, we've been talking about this a little bit as we've gone on. But if I look at the limit of this function as x approaches negative 2 from the left, there is nothing to the left of negative 2. So as I approach negative 2 from the left, the function doesn't even exist here. So there's nothing to say about the limit. There's no limit. But as x approaches negative 2 from the right, it's approaching 0. As we approach positive 2 from the left, the function's approaching 0. And if I'm approaching positive 2 from the right, there's nothing here. So that limit would not exist. And this is a semicircle. That's the equation of that semicircle given. So just a little throwback there. So some more practice problems. What if I wanted to find the limit of this function as x approaches 0 from the left versus 0 from the right? Well, from the left, this function is, as it gets close to 0, is approaching negative 1. From the right, as this function approaches 0, it's approaching, from the right, it's approaching 0. So what that means is the limit as x approaches 0 of the function does not exist, because the left-hand and right-hand limits are not the same. But this is how we can evaluate left and right-hand limits, again, which is a little bit of a review because we've been touching upon it here and there. You don't need to write this down, but this is another book definition that I just want you to be aware of, and the existence of a limit. So just trying to think about how do we know if a limit exists. Theorem 2.10 states that let f be a function and let c and L be real numbers. The limit of the function as x approaches c is L if and only if. So if these things are the case, the limit will exist. If the limit from the left approaches L and the limit from the right approaches L. So from the left and right of c, we're approaching the same value. So earlier in the year I said the limit exists if the left-hand limit equals the right-hand limit, and this is a theorem stating that. And so this is how that theorem looks kind of like in the textbook. So now we're going to decide whether the limits exist analytically. So without drawing a graph, we're going to see if we can find out what's happening here. So when I'm trying to find out if the limit exists, let's start off by finding out, there's some hints here, boundary points and undefined points. In this function that I'm given, are there any points where the function's undefined? And so as I'm looking at it, I see these two rational functions, and those things are going to be undefined when the denominator is 0. So if I want to find out where the function's undefined, because there'll be a discontinuity there, when does that denominator equal 0? So if I were to look at x squared minus 9 equals 0, that's when x squared equals 9, and that's at plus or minus 3. So apparently it looks like at plus or minus 3 the function is not going to exist, but this function only is effective, or only takes place when x is less than 1. So when I say, let's say 3 and negative 3, the function will never take on the form of x plus 3 over x squared minus 9 when x is 3. It's only when x is negative 3. So this one is not valid here, but here the function, that's a value that's less than 1. The function doesn't exist at that point, so we're going to have a discontinuity there. The second function, x squared minus 2, or the third part of the piecewise function, if I want to find out when that equals 0, that's when x equals 0. But this function only takes on this form when x is greater than 1, so we actually don't have to worry about that. Okay. So now the only other place where we might have a discontinuity of these functions is the boundary points, where they all kind of meet, which is at 1. So we're going to take some time to look at what's happening at 1. So at x equals 1, I'm going to go through that continuity test. So does f of 1 exist? What is the limit as x approaches 1? And does 1 and 2 equal each other? So that's what we're going to look for. Well, f of 1, if I plug 1 into my function, I get 2. So right off the bat, I know f of 1 is 2, the function exists. Now what's the limit as x approaches 1? So we want to find out what's happening to the left of 1 and what's happening to the right of 1. Well, if I'm to the left of 1, my function is going to take on this rule right here. So if I were to plug 1 into that, that's going to tell me what it's approaching. So if I look at x plus 3 over x squared minus 9, and I'm going to plug in x equals 1, right? So this is the limit of the function as x approaches 1 from the left. And if the limit from the left and the limit from the right are equal, we know the limit exists. So I'm going to plug 1 into this. 1 plus 3 is 4. 1 squared minus 1 is negative 8. So that equals negative 1/2. So the left-handed, this is the left-hand limit LHO. Let's look at the right-handed side, the limit from the right. So now I'm going to see what is the limit of my function as x approaches 1 from the right. And from when I'm just bigger than 1, I'm going to use this rule for the function. And so if I plug 1 into that, I'm going to get 1 squared minus 2 times 1 over 2 times 1. It's going to give me 1 minus 2 is negative 1 over 2, which is negative 1/2. So the limit from the left equals negative 1/2. The limit from the right equals negative 1/2. So if the left-hand and right-hand limits are equal, then the limit exists and it's equal to negative 1/2. So what that implies is that the limit does exist and it equals negative 1/2. So the function exists, the limit exists, but do the limit and the function agree with each other? And in this case it's no. F of 1 does not equal the limit of the function as x approaches 1, because 2 is certainly not equal to negative 1/2. So we have a discontinuity here. X equals 1 and x equals negative 3. So at x equals negative 3, we knew that the function doesn't exist there. And at x equals 1, that's the other place where we have a discontinuity. What types of discontinuity do we have? Well, let's see here. The limit from the left and the right are approaching the same value. So my function as I approach 1, so if this is negative 1, that's positive 1. So the function is approaching 1/2. And then at specifically 1, the function's value is 2. So at x equals negative 1, this is when we have removable discontinuity. At x equals negative 3, what's happening? Well, let me look at this function real quick. Do we have a hole or do we have an asymptote? And if I factor the bottom, I'm going to get x plus 3 times x minus 3. And then the x plus 3's divide out, so this is really just 1 divided by x minus 3. And so if I plug 1 into this now, if I plug 3 into this now, this is going to give me 1 over x plus 3. 3 minus 3 is 0. Oh, sorry, negative 3. X equals negative 3. Because that says negative 3. So if I plug in negative 3 minus 3 is negative 6. So what we have here is a hole. And the hole is, so the function is going to approach negative 3, comma 1, 6. So at negative 3, the function is going to approach this negative 1, 6. Kind of keep doing something. So again, that's also going to be removable discontinuity. We just need to define another point here where, when x is negative 3, the function equals negative 1/6. And then that would be the fourth part of the piecewise function that would make it continuous. All right. Another example. So given this piecewise function, let's look at the limits analytically. What is f of 3? F of 3, I have to look at the value of the function when x equals 3, and that's going to be the one that has the inclusive symbol, which is this part right here. So that's just going to be whatever 3 squared minus 5 is, which is 9 minus 5, which is 4. The limit as x approaches 3 from the left, so that's the numbers right over here. The 2x minus 1 part is the part to the left of 3. So if I look at what's happening around 3, I'm going to use that piece of the function, which is going to be 2 times 3 minus 1, which is 6 minus 1, which is 5. The limit from the right to the right of 3, we use this top piece because that's when we're 3 or bigger. And that's going to be 3 squared minus 5, which we already did, is still 4. So the limit from the left and the limit from the right are two different numbers. So the limit does not exist. And the function is certainly not continuous. Not that we were asked that, but just using the piecewise function to evaluate limits. Piece of cake. If I were to do it graphically, not bad. In this situation here, see if you can figure out where the function is discontinuous, and then I'll answer it in a second. So I see 3 points. Right here, the function doesn't is discontinuous. That's non-removable because you can't just fix that by moving 1 point. So it's discontinuous. 1, 2, negative 3. At x equals negative 3. Anywhere else, I would say right here we have a jump. So that's at x equals 1, 2, 3, 4, 5. At 5 here is it discontinuous, and yes, this is not a jump discontinuity, or this is not non-removable, this is removable. If we just move that 1 point up there, we'd be okay. But at x equals 5, the function is discontinuous. So just an FYI, these two are non-removable. And this one is removable. Okay. Alright, and I think I have one more example. Yeah, we're going to stop after this one. So here's a piecewise function, and it wants to find the value of a that'll make it continuous. So for this to happen, we need f of c to exist. In this case, this is a quadratic and linear function. The only place I need to worry about is the boundary point, which is at 1. So we need f of 1 to exist. We need the limit of the function as x approaches 1 to exist. And we need those to agree with each other. So we need f of 1 to equal the limit of the function as x approaches 1. So in this case, f of 1 is, if I plug in 1, then I got to use the top piece. 3 times 1 squared, which is 3. So f of 1 is defined. Does the limit exist? So we got to look at the left-hand and right-hand limits. So I'm going to look at the limit of the function as x approaches 1 from the left, and the limit of the function as x approaches 1 from the right. So from the left, I got to use this bottom piece. So if I plug in 1 to that, that becomes a times 1 minus 4, which is just a minus 4. The limit from the right is this top piece again, and I know that's 3 times 1 squared, which equals 3. Now, for the limit to exist, which I have to have happen, the left-hand limit and the right-hand limit need to be the same. So we need the left-hand limit to equal the right-hand limit. In other words, I need a minus 4 to equal 3. In order for that to happen, think back to your algebra skills, a has to be 7. So if a is 7, then this limit from the left is going to approach 3, because 7 minus 4 is 3. The limit from the right approaches 3, and the function equals 3 at that point. So then that'll make the limit exist, and then the limit will equal 3, which is what we need it to exist. So at a equals 7, we'll get that to happen. All right, so we'll stop there, and we'll get some practice doing this stuff in class. Again, consider subscribing, ring the bell for notifications. It really helps out the channel. If you have any questions, feel free to leave a comment. I love to hear your perspectives. Also, this video was brought to you by Raid Shadow Legends. Play today.